Welcome everybody to the May 2017 meeting of the Space Association of Australia. Sorry about all the popping and sound checks, but we've got some new equipment, as you can probably see. Hi everyone, my name is Peter Howard. I'm the President of the Space Association, newly re-elected. We had our AGM last month, and I want to put on the record now, Russia had nothing to do with my re-election, okay? That guy, that Igor. I'm still waiting for the money, Igor, but anyway. He was overseas. Yeah, talking to Vladimir. There you go. Well, thanks everyone for coming out tonight. We had a really big and special night on tonight. Very special guests come along to have a chat to us. But just to give you an introduction to us and what we do, for those who haven't been here before, we do these monthly meetings here at the Caulfield RSL, and we also have a weekly radio show called The Space Show on 88.3 Southern FM, and it's also streamed online at southernfm.com.au, so if you want to listen to that live, or you can also podcast it as well. So we've got a few little things that we'll take care of initially. Sounds really tinny. As I say, we had the AGM last month. Sounds like I'm talking like Mickey Mouse. And so we re-elected the committee, and the committee, myself, the president, Michael Abdilla as vice president, Ashley as our technical guru over there, Andrew as the radio station guy, Tim as our treasurer, and John Coleman. I don't know what John Coleman does exactly, but he hangs around a bit. No, he's the secretary of the organisation. And Len, of course, he provides our What does he do? Yeah, he provides our spiritual and ethical guidelines on what we do. So he calls it out. So so a good committee. So we'll have fun. By the way, if you didn't see the sheet on the way in, there's a sheet we've got going around here, which has got. If you haven't already submitted your details, you'll get a Reader's Digest subscription. No, you'll get information about our upcoming meetings and activities. One of our activities, which we've been putting a fair bit of work into, actually happens this coming Friday night, May the 26th. We're partnered with a company or an organisation called Moonshot X and the Carlton Collective. We're I'll bring that up actually. Stand by, caller. Where's the web browser mic? There we go. Down here. Cool. Okay, so it's this. That sounds better. Friday night, we've had this event we've called the Australia in Space, what the new space industry means for Australia. It's on the back of the Space Industry Association of Australia, which is, as the name of businesses in Australia in the space sector have got together to form an industry lobby group. Now, they released a white paper just over a month ago now, calling for, among other things, the establishment of an Australian space agency, streamlining legal and other structures within government to be able to do space activities in Australia. So what we thought we'd do is we'd help that effort along and bring in along some experts in the field who have been leading voices in the field. So we've got Peter Nikoloff from the Space Industry Association. He's going to give us a quick overview of the white paper itself. And by the way, if you go to our website and go to this page, you can go to a link and download the white paper and read it for yourself. It's quite good reading. We've also got Professor Andrew Dempster, who's the director of the Australian Centre for Space Engineering at the University of New South Wales. He's been a leading voice and has published a number of articles in The Conversation and other media calling for a space agency and space activities to be really pushed forward in Australia. We also have Andrea Boyd, who, for those who don't know, is an Australian. She's from South Australia. She's currently working at the European Space Agency in Cologne, and she's actually a flight controller working on the International Space Station. So there's an Aussie voice talking to the astronauts and cosmonauts and other people up there, whatever they call themselves, at the European Astronaut Centre. So she's going to be along. We've got Dr. Tim Parsons, who's the founder and CEO of Delta V, which is a space startup type of organisation in New South Wales. And we've got also Dr. Katie Mack, who's here tonight with us. She's going to be part of the panel discussion. So we're going to have a presentation from each of those speakers and then a panel discussion with all of the speakers on stage. So that'll be an opportunity for people to ask questions either in the audience or via Twitter, etc., etc. So it should be a really good evening. We strongly encourage everyone here and bring along your friends. It's a free event. This website here is the Eventbrite website. There's a link from our Space Association page, but if you do a search on Eventbrite or even go to our Facebook page, you'll find links to that there. So click on it, register, just gives us an idea of how many people are turning up. We've got a capacity of 120, and I think we're getting up close-ish to that number, but so come along. It'll be a good night. So that's kind of what we're doing there. Now, this is part of the association's brief. What we do is to promote the benefits of space and space activities, particularly in Australia. And as members of the association, the people in the room here are members, your membership fees obviously goes into helping us fund this event, this monthly event here, the meetings, the radio station, but also doing these special events. And what we've actually done is we've sponsored 2 of these speakers to fly from interstate to come along and speak at this event. We figure that's part of our contribution to the space scene in Australia here. So your membership fees, for those who don't know, full membership fee for an adult is $50 and concession membership is $25. And once again, you can go to our website and join up online. We'd welcome that. So what else have we got now? Okay, just a couple of little things. As people may or may not know, we've been selling some things on behalf of a collector. And there's some items down here on the floor with prices and names, some pretty unique stuff. If you're interested, have a look, etc., come and see me. The last thing is this box, this mystery box on the floor here, is a box full of space collectibles, but it's sealed. So what I've been involved in this group called Collect Space. It's a collector's website, and I'm a member of it. And so it's got this, what they call a space grab bag, the Australian space grab bag. So what happens is there's a whole bunch of really cool stuff in there, and it's been shipped around Australia, and it's come to me. And the idea is you take a couple of things out and you put a couple of things in. So it might be autographed books, photographs, it might be some unique space-related things. So I've got it. I've taken a couple of things out. I've put a whole lot of really cool things in. So what we're doing here is, if there's space collectors in the audience, you remember the association. Mike's actually taking it this month, but he'll bring it back next month. And if you're interested, let me know. It's for members only, but I'll tell you, there's some cool stuff in there. It's sealed, you can't open it tonight, so sorry about that. All right, so I think I'm done for that. So now to our feature speaker. So I'm going to, I'd like to introduce you to Dr. Katie Mack. Tonight she'll... I'm hearing voices in my head. What's going on? So tonight's talk is described as Dispatches from the Dark Universe with Katie Mack. Katie will shed light on the current state of modern cosmology, the Big Bang, and the ultimate fate of our universe. So I think we've all got a bit of an interest in that subject. So Katie is a theoretical astrophysicist. Her work focuses on finding new ways to learn about the early universe and fundamental physics using astronomical observations, probing the building blocks of nature by examining the cosmos on the largest scales. Throughout her career as a researcher at Caltech, Princeton, Cambridge, and now at Melbourne University, she has studied dark matter, black holes, cosmic strings, and the formation of first galaxies in the universe. Katie is also an active science communicator and is passionate about science outreach. As a science writer, she has been published by Slate, Sky and Telescope, Time.com, and other popular publications, and has been a columnist for Cosmos magazine. Katie is lesser known, but nonetheless fortuitous claim to fame, and maybe she'll elaborate on this later, I'm not sure. She's got a connection to the safe splashdown of the crew of Apollo 11 in 1969 after the moon landing. So please join me in welcoming Dr. Katie Mack. Mike? Stand by, we're just going to alter the technology. Testing. Does that sound better? How does that sound, everyone? Sound okay? Sound better than the other mic, or about the same? All right, we're going to go with this. Katie? Okay. Someone's got that screen. No screw-in thing on that.
All right. Whoa, that's loud. All right, how's that? Is that ridiculously loud, or is that all right? Okay. right, so the first of all, thanks for having me here. It's always fun to come and talk about the universe. The stuff I'll be talking about today is, so I say the dark universe. What I mean by that is the parts of the universe we cannot see, potentially cannot know, and sort of where the edges of our knowledge are. The work that I do is cosmology. So if you're asking what cosmology is, it's the study of the universe as a whole, from the beginning to the end, how it changes over time, what it's made of, really trying to answer the big questions. Where did the universe come from? Where is it going? What does it all mean? So that's what I do. That's my job. The main thing I study is dark matter, and I'll talk a little bit about that later on. But I've also done a lot of work on the beginning of the universe. I'm working on a paper now about the end of the universe. So really the whole span. So I'm going to talk about what the universe is made of, what's in it, what we as cosmologists study. So you've probably seen pictures like this. This is a beautiful image, the Hubble Ultra Deep Field. I think this is actually the extreme deep field. There are a few different versions. And in this picture, almost everything you see is a galaxy. That's a galaxy, that's a galaxy, that's a galaxy, that's a galaxy. This is a star. That's a star. There are a few of them, but it's almost everything in there is galaxies with billions of stars of their own. And if you look into the night sky, you can see gorgeous things like this. You can see the sort of wonder of creation. And this is just window dressing. Most of the universe looks like this. Most of the universe is entirely invisible to us. And we're starting to understand a little bit about it, but we cannot see it, we cannot touch it, we cannot interact with it. Now the first thing is dark matter. This is the main thing that I work on. Dark matter distinguishes itself from regular matter by being invisible. It's something that has mass, it interacts with gravity, but it doesn't seem to interact with light. It doesn't seem to interact with electromagnetic force at all, which means that if you tried to touch it, you wouldn't be able to do that, because when you touch something, it's the electromagnetic repulsion between the thing you're touching and your hand that allows you to do that. Dark matter doesn't seem to do electromagnetism, so it's unseeable and untouchable. So how do you study something that you can't see? Well, this is a little illustration. If you're in the back of the room, you might not be able to see the person in the center of this image swirling their hands around, but you can see the fire moving in a circle. And if you didn't know what was going on, you would figure there's probably something happening. There's probably something making the fire do that, because that's not how things work in the universe. Things don't just move around on their own, and that's basically how we know about dark matter. We see things that do emit light moving in ways they should not. We also see sort of distortions of things that emit light. So it's by looking at the things we can see that we learn about the things that are not, that we can't see, that are there anyway. And one of the first people to show us this was this person, Vera Rubin. She passed away recently. But she was one of the people who first gave us good evidence of the existence of dark matter. She was looking at spiral galaxies. This is a spiral galaxy very much like our own. You have a sort of core bulge in the center with a lot of stars and dust and a massive black hole, and then you have these spiral arms with stars. And she was looking at how these things rotate. They don't rotate like this exactly, but that kind of thing. Everything circles around the center. And by watching the way that the stars went around the center, she was trying to figure out, how the mass is distributed in the galaxy. The idea being that if you just look at a picture like this, you see there's a lot going on right in the middle, and the spiral arms are really very thin, very light. There's not a whole lot there. So if you go farther out in the galaxy, everything should be moving slower and slower, because there's just not as much gravity holding it in. It's farther away from where most of the mass appears to be, so it should be that the stars out here are going a lot slower than the stars in the center. And she found that all of the stars, as far out as you can see, are going about the same speed, which is kind of like if you're this kid pushing the merry-go-round around and you go too fast, this little child will fly off. He cannot hold on that tightly. And that's what should have happened to the stars in the galaxy as it's spinning around. These stars toward the outside can't be going around that fast if all they're being held in by is the stuff you can see. So there has to be something extra holding that stuff together. And what that is dark matter. That's the best hypothesis we have for why the stars toward the edge of a galaxy can be going just as fast as the stuff in the middle. The idea is that there's just way more matter there than we thought. It's holding it together. It's this sort of spherical-ish blob of matter in which the tiny little galaxy is embedded. And the dark matter extends far, far beyond the edges of the light that we can see. And we think that every galaxy that we know about, at least every reasonably large collection of stars, seems to have a big collection of dark matter, and dark matter seems to be most of the stuff that's out there. Now, that's only one piece of evidence for dark matter. There are a lot of different pieces of evidence. One of them is from gravitational lensing. You might have seen an image like this before. This is a sort of illustration of Einstein's picture of gravity, where space-time is a sort of fabric that can be flexible, and if you have a massive object, it creates a kind of dent in that fabric. And you have to kind of imagine this as being one dimension up, so it's more that space-time kind of gathers around the thing rather than pulling down. But what it means is that if you're trying to move past that, you get deflected. So the famous physicist John Archibald Wheeler said it like this: matter tells space-time how to curve, space-time tells matter how to move. What he means is that if you're some little object trying to move past something that has gravity, because it's curving space-time, it's not possible to move in a straight line. You get kind of deflected around it. Turns out that that's not just true for objects moving through curved space-time. Light also moves on curved paths when it's moving through curved space-time, because it can't go straight when space itself is bending. And so we get a phenomenon known as gravitational lensing, where if you have a very massive object, say a cluster of galaxies, and you have something in the background, the light from that thing will be bent around by that massive object, and you'll see the light in two different directions. So if you're sitting at the Earth over here, and you're looking toward that distant galaxy, because the space-time in between is bent, when you look this way, you'll see a light beam from that galaxy, and when you look this way, you'll see a light beam from that galaxy. You'll see the galaxy in more than one place. You won't see it in the position that it's actually in. And we can see this in the sky. This is a picture of some massive cluster of galaxies, and these little arcs here are distorted images of the stuff in the background. It's a lot like if you look through the bottom of a wine glass and you see sort of arcs of light as you hold it up to a candle or something like that. You get a very similar phenomenon in space, and you can see really dramatic images. This is a galaxy here, and its image is being stretched all the way out there. This is all the same galaxy. It's in the background, and the light from it is just being bent around and distorted in a really grotesque way. Over here, you have the same thing. This galaxy and this galaxy are the same, but you're seeing multiple images of it. Here's another great example here, where the galaxy gets sort of stretched out by the objects in the middle. And sometimes if you have the alignment just right, you can get what's known as an Einstein ring, where you have a very massive, sort of very symmetrical object, where this galaxy is right behind it, and so it gets stretched out like that. And then you can get some more whimsical little happy face gravitational lenses. The point is that, yes, question? I mean, this is all visible. These are all visible images. You can see lensing if you look in radio as well, but these images are mostly from the Hubble Space Telescope. And what this does is it doesn't just give us, cute little happy faces in the sky. It also tells us about the matter that's there that we can't see, because gravitational lensing doesn't care whether the matter is emitting light. All it cares about is how much it's bending space. And so you can actually weigh galaxies and clusters of galaxies by how distorted they make the things behind them. And so you can see when you look at these kinds of images that if it were just the stars that we can see doing the providing the gravity, it wouldn't be enough. You need something extra there that's also bending space with gravitational lensing. So there are a few other pieces of evidence for dark matter, but those are some of the main ones. We have a pretty good reason to believe that most of the matter in the universe, something like 85% of the matter that's in the universe, is completely invisible to this dark matter. Now, dark matter is still a small fraction of what's in the universe total. Most of the universe is what we call dark energy. Now, dark energy is the dominant component of the universe as far as we can tell, but we really, really don't know what it is to a much greater degree than we don't know what dark matter is. We know a lot about dark matter. We can see where it is. We can see what it's doing. We can see model it in computers and see how it clumps together and forms the sort of structure on which all of the beautiful things in the universe we see are built. Dark energy is what we call the thing that makes the universe expand faster than we expected. So the universe is expanding. The way the universe is expanding is you have a bunch of galaxies and they're moving farther apart from each other. This is my very technical movie of this. And the expansion of the universe should be slowing down. Based on everything we understand about physics, as the universe is expanding, which the expansion was sort of set off by the Big Bang, the gravity between the galaxies should kind of slow that expansion down. Maybe it'll keep expanding forever, maybe it'll go to a big crunch, but it should be slowing down. However, in the late 90s it was discovered that it's not slowing down, it's speeding up. And there is something out there, we call it dark energy, that is causing the expansion of the universe to accelerate. It might be what's known as a cosmological constant, which is just a property of the universe that Einstein wrote into his equations that says that there's some extra sort of term in the equations that balances out gravity and pushes things to expand faster. But whatever it is, it says that the universe is expanding faster and faster, and as a result, our galaxy, or our little group of galaxies, is getting more and more isolated. All of the other galaxies are moving away from us. Not that they don't like us, it's that everything is moving away from everything. And over time, everything is getting more and more isolated. Things that are already gravitationally bound will stay gravitationally bound. So our galaxy will stay together. We're going to collide with the one next door, Andromeda, in 4 billion years or so. That'll be really exciting. And the local group of galaxies will stay as a clump. But eventually, that'll be all we can see. In several billion or trillion years, the sky will be dark outside of our galaxy. And if dark energy stays the same as we see it today, if it just keeps causing acceleration, if it is a cosmological constant, then the ultimate fate of the universe is that all of the luminous things in the universe, all of the galaxies, will become more and more isolated, the stars will burn out, and everything will just fade away. It's known as the heat death. Eventually, even black holes will evaporate, protons will decay, the universe will be empty and cold and, unable to continue anything. That's if dark energy is what we think it is. We don't really know what will happen with dark energy in the future. There are some other possibilities. Some of them are more cheerful than others. One of them rips the universe apart. I won't get into that, but at the moment, this seems to be the most likely fate of the universe, that it just gets more and more empty and more dark and ultimately fades away. So that's dark energy, and dark energy appears to account for something like 70% of the energy of the universe. So it really dominates everything else and will become more and more dominant over time. So just to review that, dark matter is something that creates these sort of dents in space-time, and dark energy is something that kind of stretches space-time out. And if you put that all together, then you get a pie chart of what the universe is made of. These are figures from the Planck satellite from a few years ago. So the numbers change a little bit depending on which observation you're looking at. But basically, vast majority of the universe is dark energy, then dark matter, and then there's this tiny little sort of 5% slice which is the stuff we remotely understand. This is everything we see in the night sky, everything we can touch, everything that fits into our models of how physics works on the particle level. So we have a very high precision picture of what the universe is made of, but these bits here are still really big mysteries that we're still working on. So that's kind of what we know. I also wanted to talk a little bit about sort of the edge of our understanding. One of the questions that I'm asked a lot is, if the universe is expanding, what is it expanding into? Is there an edge of the universe? Is there something outside of the universe? And to answer that, I'm going to first talk about something called the cosmic microwave background. Now, this is a picture of the cosmic microwave background from the Planck satellite. This is a projection of the whole sky, so it's kind of like if you take a projection of the globe like that, except it's the sky. So this is a sphere around us, and this is a picture in microwave wavelengths, and those little colored dots are temperature. These are fluctuations in the temperature of the sky at the level of 1 part in 100,000. And this is what we're looking at here is fluctuations in the afterglow of the Big Bang itself. So if you think about when we look into space, we're looking back in time when we look into space. That's how it works, because there's a delay in the speed of light that tells us that the farther away we look, the farther back in time we're looking. Turns out that light travels about a foot per nanosecond. So as I look toward the back of the room, I'm looking at about maybe 40, 50 nanoseconds ago. And as I look at the sun, which I shouldn't do without protective eyewear, I'd be looking at 8 minutes ago. If I look at a distant galaxy, I might be looking at millions or billions of years ago. And so it stands to reason that if you look farther and farther back, you're looking closer and closer to the very beginning of time, the very beginning of the universe. The universe is about 13.8 billion years old. And so if we can look far enough, we can look at parts of the universe that are still in the very, very beginning stages. We think that at the beginning of the universe, there was this hot, dense state, this primordial plasma called the hot Big Bang, where the universe was very hot, very dense, and it's been expanding since then and cooling down. And so if we look far enough away, we're looking to the time when that part of the universe that we're seeing at the very distant reaches of what we can observe, that part of the universe is still in that plasma state. So we can actually see that hot Big Bang time of the universe, because we can see parts of the universe that are still in it. We can see the edge in time of the primordial fireball universe. And that's this. This is the radiation from the cooling universe, from just when that plasma state was cooling down enough for light to travel away from it. Like looking at the edge of the sun, for example, where you can't see the center of the sun because you'd have to look through this hot plasma. You can kind of see the edge of the sun because that's where it becomes, diffuse enough that the light can travel. It's the same kind of thing looking at the beginning of the universe. And so this is an image of that. And the fluctuations that we see here are little tiny fluctuations in the density of different parts of the universe. And if we zoom into these little density fluctuations are the things that are going to collapse via gravitational collapse. They're going to come together with gravity and form the seeds of galaxies and galaxy clusters over time. So we're looking at a very distant part of the universe, but if we look at these little spots, those little spots are going to turn into galaxies and clusters of galaxies and all of the structure that we can see. And when we model that sort of thing in a computer, this is a model of the cosmic web. This is a simulation that's only dark matter, but it shows density fluctuations. So you have here a sort of cluster of galaxies. You have these filaments, big voids where there's not a lot of matter at all. And that all grows out of those tiny fluctuations in the cosmic microwave background, in the sort of edge of that fireball. And when we do these simulations, it looks a lot like the actual universe we see when we count up galaxies. And based on all of the observations we have, it looks more or less the same as far out as we go. There seems to be a lot of uniformity in the sense that there doesn't seem to be an edge. It seems like the structure of the universe just kind of keeps going. And this is known as the cosmological principle, or the Copernican principle, the idea that we're not in a special place in the universe. There doesn't seem to be a place where if we keep going that way, everything changes. There's an edge in time, in the sense that we can't see beyond the beginning of the universe. So we have a cosmic horizon in the sense that if we try and look too far, we get to the point where the universe hasn't started yet, and we can't see beyond that. We can't see beyond that primordial fireball state. But in terms of space, it doesn't seem that there's any distinction between different parts of the universe in terms of the structure and the sort of statistical layout of the universe. Everything kind of looks the same. So as far as we know, there's no edge to the universe. There is an edge to understanding. We cannot look beyond something like 46 billion light years away, because if we tried to look beyond that, we'd be looking so far back that the universe hadn't started yet. Sorry, I'll just wait a moment while the things are collected here. Okay, so we think that there's basically no edge to the universe itself, but there's definitely an edge to our understanding, simply because the universe had a beginning, and we can't see beyond that. But one of the things that we can do is learn something about the universe by looking not at the largest scales, but at the smallest scales. So as a cosmologist, I'm interested not only in sort of the large-scale structure of the universe, but what it's made of on a sort of particle level, on a subatomic level. I'm interested in the fundamental physics of how the universe works, and particle physics is a big part of that. And we're learning about the beginning of the universe and the structure of the universe through particle physics. One of the tools for that is the Large Hadron Collider. This is actually data from a collision event in the Large Hadron Collider. This is the kind of collision event that makes the Higgs boson. And what we do with the Large Hadron Collider is we take protons and we slam them together and we see what comes out. And we learn about the structure of particle physics that way. We can also learn about how physics works at very high energies, very high densities, as we had in the beginning of the universe. And so we can kind of recreate some of that primordial plasma that we can see with the cosmic microwave background. We can recreate that a little bit in these colliders. But we also can just learn about how particle physics works. And we get things like this. This is the standard model of particle physics. There's the Higgs boson, the newest edition. This is all of the particles that we know about in the universe that we've observed. This is the green ones here are the leptons. The electron is the most famous one. There's neutrinos, cousins of the electron. There's the quarks, which make up protons and neutrons. There's the gauge bosons. These are the force carriers, things that transmit electromagnetism, strong, weak force, all of that. And then the Higgs boson, which is responsible for some of the interactions that allowed some of these particles to gain mass in the early universe. This is the standard model of particle physics, and there are numbers on these particles, and those numbers represent sort of what we know about the parameters of the standard model of particle physics. This is a very well-tested model. I mean, finding the Higgs boson, the final piece of this model, the final piece of our understanding of particle physics, was a huge success. And every test that we've done with particle physics has given us reason to believe that this is a really solid theory. However, it tells us some rather disturbing things. And one of them is this picture. So this is a plot from a recent paper from 2012. This is a plot where we have the Higgs mass, the mass of the Higgs boson on the bottom, and the mass of the top quark on the y-axis. And these different colored regions are things that we learn about the sort of basic structure of the universe from measuring these quantities. And this little region up here is where we think sort of our universe lies in this picture, where if we take the masses we've measured of the Higgs boson and we take the masses we've measured of the top quark, we get to that point. And that's a point that suggests that our universe is not stable. So if we were solidly in the green region, we'd been in a stable universe. We're in the yellow region. That's metastability. It's not instability. Which, if we found that we were in an unstable part of the universe, then that wouldn't make sense because clearly we exist. But metastability is also kind of troubling. And what metastability means is that we have a picture sort of like this. So this is a drawing from a paper in 1980 that I'll quote a little bit later. States of the universe. These different states of the universe tell us things like the parameters of the standard model of particle physics. Those numbers on that plot, depending on where we are, whether they were in this state or this state, those numbers will be different. Things like the gravitational constant will be different. The charge of the electron will be different. All the parameters of particle physics as we know it will be different if we're in these two different states. And these are different states called vacuum states. So we live in one of these vacuum states, and metastability suggests that the vacuum state we live in is this one over here. It's the so-called false vacuum, which means there's a true vacuum over there. And the problem with having a true vacuum when we live in a false vacuum is that it's possible to move from one to the other. The most straightforward way to do that would be to have a very high energy event, which sort of kicks us into that other vacuum state. People used to worry about that with particle colliders. Those don't go anywhere near the right energies to do that, so don't worry about that at all. That can't happen. But one thing that can happen, which is also troubling, is based on the fact that our universe is fundamentally quantum mechanical, which means that we could just kind of quantum tunnel into that other vacuum state. So we might be perfectly happily living over here, and then suddenly we can tunnel right through that barrier. Quantum tunneling is a thing that's observed in particle interactions all the time. Could happen on the scale of the whole universe. And we could end up in this true vacuum state. And that's something known as vacuum decay. What vacuum decay would look like is this. You would have one point in the universe would decay into the true vacuum. It would create a bubble of true vacuum that would expand at the speed of light throughout the whole universe. And that bubble, inside this bubble of true vacuum, the constants of nature are different, which means that the gravitational constant is different, the charge of the electron is different, the spin of the particles might be different, which means that our atoms would not hold together in that new vacuum state. We could not have life or the structure of chemistry in this new vacuum state. And another thing that's just incidentally, this bubble wall has a lot of energy too, and would incinerate everything. So first it incinerates everything, and then it sort of decomposes it, right? And because it's moving at the speed of light, if it starts in one point in the universe, and we're over here, there's no possible way we're going to see it coming. It's the speed of light, like it would just happen. So that's disconcerting. And based on our understanding of the standard model of particle physics, there's nothing to say that that can't happen. There is a sort of a mathematical argument that the decay constant, the time that between now and when it decays would probably be very long, longer than the age of the universe. It's not something that's going to happen tomorrow, probably. But it's a quantum mechanical process. We can't really say for sure that it couldn't happen right away. And if it does happen, it's obviously bad for a couple of reasons. One is this fact that we couldn't survive in the true vacuum. Even if we survived being incinerated by the bubble wall, we couldn't survive in the new vacuum. But also, there's this paper in 1980 by Coleman and DeLucia, which suggested another reason this would be bad, which is that they calculated that the true vacuum would also be gravitationally unstable, meaning that once that true vacuum bubble is formed and envelops the universe, it immediately collapses. So obliterating everything in an even more final way, making vacuum decay a very true end of the universe scenario. It's a little unclear based on the latest data if it would really collapse immediately or not. But that's definitely a danger. And they have a description of this, a discussion of this in this paper. That's one of the most poetic pieces of physics I've ever read. So I'm just going to read you this little bit. So this is right after they calculate that the true vacuum is gravitationally unstable. They say, "This is disheartening. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps, in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated." So when we look at this picture, it is troubling. It is troubling to think that we might be in this metastable state. But what we should really take from this picture is a totally different message, which is going back to this diagram. I showed you, so most of the universe is dark matter and dark energy, and dark matter and dark energy are not part of the standard model of particle physics. The entire standard model of particle physics is in this little slice here, this bit labeled atoms. So that the picture, the diagram of where we're in a metastable state depends on the standard model of particle physics being the complete be-all and end-all of physics. It depends completely on being able to trust those calculations. And we know that can't be the whole picture, because we know that there's some other particle out there that acts in a totally different way called dark matter. We know that there's something out there called dark energy, which is changing the expansion of the universe. We know that there's more that we just can't observe right now, that we don't understand. And so as we look at things like vacuum decay, the thing we should do is not, freak out that we're all going to vanish in a puff of true vacuum, but that we really need to look into these other areas of physics and try and get a more complete picture of the universe and really understand how it all works. Yes, question. Microphone. This is basically the end of my presentation, so we can just carry on with questions if you like.
Okay. So this pie chart.
Yes.
The percentages are of the total mass of the universe, or volume?
The total mass energy of the universe. Mass energy. Yeah. So we can define a kind of energy to dark energy, a kind of energy density. With dark matter, it's easy because it's the mass of the dark matter. With dark energy, we can associate a certain amount of mass energy to whatever it is that's doing the accelerated expansion. So even if it's cosmological constant, we can assign a kind of energy density to that. And what we find is that it's most of that. So just as a side note, the reason it's called a cosmological constant is that the density of it is constant. That's weirder than it sounds, because the volume of the universe is not constant. So if you have a box this big and it's got some amount of dark energy in it, and then you suddenly make that box twice as big, now you have twice as much dark energy. And so the universe just has more dark energy in it as time goes on. And so because of that, the amount of dark energy is increasing. The amount of dark matter is not increasing. And so the matter becomes diluted over time, the radiation becomes diluted over time because the universe is getting bigger, but dark energy isn't subject to that. So as far as we know, the amount of dark energy just keeps going up, which is why it's so dominant, why it will continue to be dominant in the future. And there are even different models of dark energy that make it so that when you make that box bigger, now you have more than twice as much dark energy, and that's something called phantom dark energy, which is the kind that rips the universe apart. We don't actually know at the moment which of these cases we're in. So everything right now looks like dark energy is probably just a cosmological constant, just a very weird fact about the universe, but at the moment we can't say. So if we want to understand, how the universe is going to end, we need to understand all of these things much better. Yes?
Just a question.
Yeah.
How are you going to test this? How are you going to test?
How are we going to test the numbers? Well, so the numbers are the way we test the numbers. There are a couple of things we can do with that. One is that we look at the patterns in the cosmic microwave background. So those the statistics of those little spots on the cosmic microwave background tell us about how much regular matter versus dark matter there was at the beginning. Tells us something about the dark energy through basically understanding the shape of the universe. So that's a little bit subtle, but the universe appears to be flat in the geometrical sense, meaning that if you have a curved space, then parallel lines will come together in a curved space. So if you have a curved space, they do like that, or if you have a space curved the other way, they might diverge. And it appears that in our universe, they would go straight. So there's no large-scale curvature of the universe. The way that there's a small-scale curvature when you have a massive object, on largest scales, it's basically flat. So that tells us something about how much dark energy there is as well, because it kind of, it's one of the components that keeps the universe flat, in a sense. So we can learn a little bit about what's in the universe from looking at things like the cosmic microwave background. How we learn about what those things are is a little different. So I don't work on this part. There are a couple of different ways to learn about what dark energy is. Mainly they're testing the cosmological constant idea, so seeing if the density of dark energy really does change over time or not. And you can do that by looking at the expansion history of the universe, which you do by looking at more and more distant objects and sort of how their distance and the wavelength of their radiation changes over time. So there's relationships between how quickly things are moving away from us and how far away they are, and that tells us something about the expansion history of the universe. So we can learn a little bit about dark energy that way, and we can learn about it by studying how structures grew in the early universe, so how the first galaxies formed, how galaxy clusters formed, and the statistics of how many galaxies and clusters we see. So far, all of that is very consistent with the cosmological constant. So at the moment, it looks like dark energy might just be a sort of property of the universe, rather than some new component, really, like a dynamical field or something. In terms of dark matter, there are a bunch of different ways to study dark matter, some of which I'm involved in. So you can try to detect a dark matter particle. The way you do that is you bank on the idea that maybe dark matter can interact with regular matter through the weak nuclear force, which means that every once in a while you could have a collision between the two. And since we are living in a galaxy that's embedded in a sort of cloud of dark matter, and we're moving through that cloud as the sun orbits the galaxy and we orbit the sun, there's dark matter flowing through it all the time. And mostly it doesn't interact with us, but every once in a while maybe it could bump into some nucleus. And so you take a box of nuclei and you put it at the bottom of a mine or something like that, and you just wait for one of those nuclei to get bumped. It's called a nuclear recoil experiment. There's an experiment in Stall in rural Victoria that we're building to do just that, to look for that bump. So that's called direct detection. Then we can also look for the possibility that two dark matter particles might annihilate with themselves if they interact in a certain way. That's called indirect detection, so we can look for products of that annihilation. Basically, like if you have a proton and a positron, an antimatter version of a proton, and you put them together, they annihilate. Might be that dark matter is its own antiparticle. So two dark matter particles, if they come together, might annihilate into other kinds of matter. And if that's the case, then we can look for the results of that. So that's indirect detection. And then the third way to look for dark matter, try and figure out what it is with collider experiments. So if it's true that two dark matter particles, when they come together, can create regular matter, then maybe you can take regular matter, put that together, and make dark matter. And we're trying to do that with colliders, where basically we smash protons together, and we try and see if there's anything missing in the debris. So you create a whole lot of like, junk after the collision, and you see if any of it's missing, because it was dark matter that escaped the detector. So there are several different ways. The way that I'm interested in looking for dark matter in particular is I like to think about so the first stars and galaxies in the universe formed sort of in these clumps of dark matter at very early times. So there's a clump of dark matter, and then there's like a little galaxy or star in the middle. And if that dark matter in the early universe was annihilating with itself, then it would create a little bit of energy inside that clump of gas that's trying to form the first stars and galaxies, and we might be able to see something as a result of that in the sort of properties of those first stars and galaxies, which we can see by looking back in time very, very far with new telescopes. So that's what I'm doing. But you can also just learn about, indirectly learn about the properties of dark matter by, watching things like collisions of galaxy clusters or doing the gravitational lensing stuff and all of that kind of thing. Yes? You want to?
G'day, Katie. I'm a high school physics teacher, and I've just been teaching all of this over the last 2 weeks.
You have
yeah. My voice is louder than the microphone.
Okay.
I'm a teacher. So a million questions. Where to begin? So I'll knock it down to my top 2 or 3.
Okay.
Dark matter only interacts with, it doesn't interact with the electromagnetic force. We suspect maybe the weak nuclear force. Mm-hmm. We know about the strong nuclear force. So it's largely hypothetical, although we have some spurious evidence for it. Dark energy is an entirely theoretical concept, and you could pop in both there 3 significant figures. So there must be a model that this is based on. I mean, the stuff we do know and can see and measure, you've only got 2 significant figures. So the atoms there are all the standard model. That's the leptons, the quarks, the gauge bosons, the anti-leptons, and the anti-quarks. You're saying the dark matter is none of those. We don't even know if there's dark antimatter. So do we have any idea about the interactions between the real stuff and the dark matter? Is it possible that the spontaneous creation of electron-positron pairs that instantly annihilate each other, they come out of the quantum vacuum? Would there be a connection there to dark matter? Can you see where I'm going? Millions of questions here. This is theoretical.
Okay, so there's
where are the 3
no
significant figures from?
So this figure is adapted from a figure from the Planck Space Telescope from the European Space Agency. It's a figure that was made for the general public, and so they were not being as exact with the significant figures as perhaps you would have liked them to be. But nonetheless, there are error bars on all of these that are a % or so, based on other observations. You asked about the strong force. There's no evidence for dark matter interacting with a strong force. There's no evidence for it interacting with a weak force. There's only evidence for it not interacting with anything other than gravity at the moment. However, if it didn't interact with the weak force, it would be very hard to figure out how to get it into the universe in the first place, because we think that all of the stuff in the universe comes out of the decay of the inflaton field, which is the sort of leftover from the rapid inflationary expansion in the very, very early universe. Even if it weren't the inflaton, there's probably some kind of other interaction between dark matter and regular matter. Is this all theoretical? In a sense, certainly. However, it's also very, very observational. We have seen quite a lot of evidence for dark matter in the sense that there's a lot that really can't be explained very well without it. There's gravitational lensing, there's cosmological microlensing, which is a whole other topic. There's the statistics of the cosmomicrowave background, which don't work if all of the matter has collisions as atoms would. There's gravitational weak lensing, which can map out where the dark matter is on large scales. There's the fact that when we do simulations of galaxy formation with only dark matter, we get the correct statistics of where galaxy clusters and galaxies form, if we tried to put all of the matter as some kind of collisional matter, it wouldn't work. You wouldn't get the galaxies forming by today. So simulations also suggest that basically we can't get the kind of universe that we see right now if we didn't have some portion of the matter being non-collisional. The fact, the division between atoms and dark matter come from mostly those kinds of measurements. The division between matter and dark energy comes from measurements of the flatness of the universe and comes from measurements of the growth of structure in the universe and the expansion history of the universe. I could show you the math on that. It would take a while. But it is very, very observational in the sense that the universe does not make sense as we observe it unless we can divide it into these three subsystems, so these three classes of energy density. We have to have something that has collisions that we can see, atoms, that has to be there because we see it. There has to be something that doesn't have collisions but does have gravity, and there has to be something that contributes to the expansion of the universe and to the overall energy density of the universe but doesn't self-gravitate. So those are the main things that absolutely have to be there for our observations to make sense. It is possible to create models that alter some of this picture. It is possible to create models where instead of dark energy being a new component, there's some kind of alteration of gravity on very large scales. Those models are not favored by the data. There has not yet been a model produced of large-scale alterations of gravity that explains the observations that suggest dark energy that work as well as dark energy. You can also create models that change gravity on smaller scales that could reproduce some of the observations that we use to infer the existence of dark matter. Those also do not work as well with the data as dark matter. So as we do in science, in every possible situation, we take the data, we take the models, we compare models based on whether they fit the data better or not. So if you take two models of the universe, one that looks like this and one that looks different, this one looks better with the data. This one has a much better match to the data. It may be that in the future we'll have other models, other theories that explain the data better than this. Hopefully, we will have some models that at least are able to connect the standard model of particle physics with the large-scale structure of the universe. At the moment, we don't have that. Hopefully, at some point, we will be able to say how quantum mechanics and general relativity work together. That's a big open question. But based on the models that we have now, this is the one that works.
They both on gravity. This comes down to gravity. So we don't even have a complete standard particle model of physics. We're missing on those ones.
Well, the standard model of particle physics doesn't include gravity at all. No. Yes.
Hi. Oh, sorry. Just as an example of that, just in terms of how our understanding of this picture has evolved, I just wanted to find out how our understanding of dark energy has changed when we first found out about the accelerating expansion of the universe. Did that change our understanding of dark energy? Or is that when dark energy started to come into the picture in the first place?
Yeah, so dark energy has a funny history. The cosmological constant was part of Einstein's initial equations of gravity. The reason that he put... a cosmological constant is something that counteracts gravitational collapse, basically. The reason Einstein put that in there is because he did not know the universe was expanding. And so if you look around at the universe and you think, that the universe is static, that it doesn't change over time, it doesn't expand, doesn't collapse, then that doesn't make sense because gravity should be making it collapse. So Einstein put in a term that would counteract the gravity exactly and make the universe static. Then when it was discovered that the universe was expanding, he took out that term because you don't need an anti-gravity force anymore, you just have the sort of inertia from the expansion, and that's fine. And so he got rid of the cosmological constant. It wasn't until the 1990s where we put the cosmological constant back because the acceleration of the universe was discovered. So the sort of inertia from the expansion from the Big Bang doesn't give you acceleration. It gives you, continual expansion, but maybe always slowing down. So there were experiments to try to measure the deceleration parameter, the number that quantify exactly how quickly the universe was slowing down in its expansion. Those experiments failed because the deceleration parameter was negative, because the expansion was actually speeding up, and that was what brought dark energy into the picture, a cosmological constant or dark energy. So dark energy just means something that has this sort of negative gravity sort of behavior. But dark energy in general could be something that changes over time. A cosmological constant can't. So we talk about dark energy because it's more generic. But a cosmological constant is what fits the data at the moment. And that was discovered in the late 90s. And Brian Schmidt and Saul Perlmutter and Adam Rees got the Nobel Prize in 2011 for discovering the accelerated expansion. They don't call it a Nobel Prize for dark energy because we still don't know why the universe is expanding per se, but why the universe is accelerating per se, we do know it's accelerating. And so the discovery of that acceleration was enough to get the Nobel Prize. So even if the acceleration is because of some weird quirk of gravity and not because of dark energy or something like that, it's still a major new part of our picture of the universe.
Two questions.
Yep.
Two questions, if I may. The people who are positing that dark matter is made of particles, would that be one type of particle, or like ordinary matter, a zoo of particles, types of particle? And the second question is, can dark matter fall into a black hole?
Okay. So the first question, can it be multiple kinds of particle? Definitely. There is nothing to say that dark matter is only one kind of particle. We usually make that assumption because it seems simpler than positing a whole lot of different new particles. It seems simpler to just posit one new particle, but there could be many different particles that behave as dark matter does, as some kind of weakly interacting massive particle. But there are limits on how much they can interact with each other, because if you had a whole other sort of regular standard model of particle physics, but in the dark sector, and if those particles had a lot of interactions with each other, they could start to act like regular matter. They could have pressure. They could form disks the way that our matter does, and we don't observe that. So we can observe. We have limits on how much the dark matter can interact with itself, which suggests that if there is a sea of different particles, they don't interact with each other a whole lot. So they're not the same. They're not the same level of interactive as our own regular matter is. The question about whether it can fall into black holes, totally. It's not as easy as you might think. So I wrote a paper about trying to get dark matter to fall into black holes when I was a grad student. And the problem is that it comes down to a very related point, actually. Let's say that you have a whole bunch of gas and a black hole in the center. And you just let the gas go, it'll form a disk, because basically there's going to be some random motions in the gas, and so there's angular momentum for all the different gas particles in different directions, and there will be some sort of average rotation for that blob of gas, because there's always some kind of average rotation, and everything else will cancel out by collisions. So the ones going in orbits like that will bounce it off each other and emit radiation and cool and cancel out, and you'll end up with a disk. So this is why we have disks of galaxies. You have disks in solar systems and stuff like that. And around black holes, we often see disks of matter called accretion disks, where the matter is moving very, very quickly and lights up, and you can see X-ray radiation, and it's very cool. And you can get these bright, glowing disks of matter falling into black holes. They're sort of orbiting and gradually falling in. Dark matter doesn't do that sort of thing. So if you have a cloud of dark matter, because it interacts with itself so rarely, you're not going to have a lot of those collisions that knock things into the black hole or knock things into a disk where they can sort of, gradually go in. You're going to have a fairly stable cloud of stuff just orbiting. And until it gets close enough to the black hole to be affected by the event horizon, it's going to be very hard to get the dark matter to fall into the black hole. So accretion of dark matter into black holes is harder than accretion of regular matter into black holes, because it doesn't like to lose energy. It doesn't. It's not a dissipative stuff, is the way we say it. It doesn't have collisions, so it's harder to get dark matter to collapse, which is why dark matter ends up being this sort of puffy blobs instead of disks and stars and things like that. Yes.
Okay, we've got a person watching the stream has sent us
Okay.
2 questions.
Sure.
The first one is, what is your favourite movie? Is it Interstellar? And the second question is, do dark matter and dark energy relate to each other like E = mc squared?
Okay. My favorite movie is not Interstellar. I'm not going to say a whole lot more about that, lest I get in trouble. I wrote, if you're interested though, I did write an article for BuzzFeed about the science of Interstellar. Movies I have liked very much include 2001, Gravity, I quite liked The Martian. What else? I don't know. A whole lot of stuff. The new Guardians of the Galaxy was really good. Okay, and the other question was, dark energy and dark matter. I mean, as far as we know, there's no connection between them. There are models of dark matter and dark energy that do have like interactions between them. There are some where dark matter turns into dark energy to explain why dark energy is more dominant today than it used to be. Those models are not the sort of accepted ones. People are making those models. There's people in Australia working on it, but as far as we know, because they act so differently, because dark matter is a massive thing that sort of pulls together, and dark energy is something that seems to be completely uniformly distributed across the universe and just sort of has this negative pressure, which means that it kind of pushes things apart. We call them both dark because we don't know what they are and we can't see them, and that's really the reason that we call them dark. And so a lot of times people ask if there's a connection between them, but as far as we know, there is not.
Okay, this is my own question.
Okay.
This is probably a little bit more personal. What does your job entail? Like, what did you do today? Do you?
Okay.
Do you come up with theories and then try to use data to prove them, or do you look at the theories and use the data to try and prove or disprove those theories? Tell me how you work.
Yeah, so I kind of do. I kind of do neither of those things. I sort of sit in the middle between those things. So I call myself a theorist. I might be properly called a phenomenologist. What that means is that I talk to the theorists, mostly particle theorists, and I find out what the new interesting theories are in fundamental physics. And then I talk to the observers, and I find out what the big new telescopes are, what kinds of observations can be done, and then I try and find creative ways to connect those two things. So for example, when I was a graduate student, I was working on a project thinking about cosmic strings, which are these hypothetical sort of strings of energy that stretch across the universe that might have been produced in the very first moments of the universe and might sort of exist in the cosmos as a very theoretical idea. And then I figured out a way to test theories of that using radio telescopes and gravitational lensing. So, I'm interested in thinking about very different, new and different ways to test theories. So right now, the big project for me is thinking about this dark matter and how it affected the first stars and galaxies. And so I work with the particle theorists on what the interesting particle dark matter models are. And then I'm part of the Square Kilometer Array collaboration, which is this new array of radio telescopes. And I'm part of their collaborations to think about cosmology and the evolution of gas in the universe. And I'm trying to think how you can use the Square Kilometer Array to observe those first stars and galaxies to learn something about dark matter. So those are the kinds of things I think about. In terms of what I do day to day, I read papers, I do calculations on paper, I do calculations in a computer, I talk to my colleagues, I plan new research projects. Today I had a meeting about a CubeSat that me and some colleagues are working on. Friday I was working on a paper about a new about the science case for a new dark matter detector, where I was sort of thinking about how we could learn about the structure of the dark matter in our galaxy by doing experiments underground looking for dark matter. So those kinds of things. So it's a lot of computing. I write a lot of code, and I do a lot of writing down equations, and I do a heck of a lot of talking to people, and that's most of my job. Yes.
You have been able to detect gravitational waves. Can you comment on how do you think and help cosmology?
Gosh, I wish I had another half hour to talk about gravitational waves. Gravitational waves are awesome. We can learn about many different things. One of the things I'm really excited about is using gravitational waves to learn about black holes, and not only sort of the fundamental physics of black holes, how they work, what their structure is, but also how they're distributed in the universe and how they come together and how they make bigger black holes when they collide. And, are there a lot of small ones and big ones, or are there medium-sized ones, and how do you make galaxies out of collision? When two galaxies collide, they each have black holes in the center, supermassive black holes, and so those collide, and you can learn about galaxy formation from that. So all of those things are fascinating, and in the fairly near future, we should be able to use gravitational waves to learn about how galaxies came together over time, and potentially learn something about dark matter from that too, because that can affect how the galaxies come together. So that's something that I've been talking with some colleagues in the States about, is thinking about how to learn about the formation of galaxies and dark matter from black hole collisions and gravitational waves. But yeah, the gravitational wave discovery was probably the most important physics discovery that's happened in my lifetime. So it's very, very exciting. But I wasn't involved in it at all, so I don't give talks about it very much. But it's very cool. So you can ask me about that later if you're interested. Yes.
Accelerates towards you. I think you get started that question. I just didn't really understand it, basically.
Yeah,
I think it has cosmology.
Yeah, so there was a paper recently about negative mass. So they took a special system called a Bose-Einstein condensate, which is a way of collecting a liquid helium type material, where you have a whole bunch of atoms in a very cold state, all in the ground state. So they built this Bose-Einstein condensate, and then they messed around with the sort of parameters of it to make a kind of virtual particle type thing that moved in a funny way. And it was they spun it as being this really big discovery about negative mass, but it was more a sort of I think it was a little bit oversold. I think it was a very interesting result. It was a very interesting experiment, but it was more about sort of properties of a specially prepared system rather than a new particle. So it definitely was not a new particle. It was nothing fundamental, but it was an interesting way of putting together a system such that it would act in a sort of strange way by having sort of weird wave dynamics inside it. It's a condensed matter experiment, and I'm not super well versed in that, but it's a very interesting experiment, but nothing to do with cosmology as far as I know. Yes?
So I've got two more questions from the chat.
Okay.
So if the universe is unbounded and flat, isn't it therefore infinite?
Yeah, it might be infinite. We don't know. We don't have any reason to believe it's not infinite. It might bend back on itself, but if it does, it's so far away that we can't see the evidence for that. So, we have an edge to how far we can see. So anything beyond our horizon, we just don't know what's going on there. And as far as we know, we have no reason to believe it's not infinite, but we also have no reason to believe it is really. So.
And the second question was, would gravity in some form encompass that entire chart?
Gravity? In the sense that, gravity has something to do with all of the things that are part of this, sure. I mean, gravity is not, as we discussed already, gravity isn't really part of the standard model particle physics. We don't have a good way of connecting Einstein's relativity to particle physics, and so it definitely doesn't fit in this part in terms of our theoretical understanding. But everything in this chart has some interaction with gravity in the sense that, I mean, dark energy just stretches out space-time, so if you want to call that an interaction with gravity, you can, but it doesn't, dark energy itself doesn't gravitate. So, I mean, gravity is a big unknown in some sense, in the sense that we don't understand how it fits together with the rest of the picture, our picture of physics.
Okay, we've probably got time for one or two more questions. If someone's got a couple of questions.
The universe is more finite than infinite?
I mean, we definitely know that the observable universe is finite in the sense that we can define a sphere of radius 65 billion light years centered on ourselves beyond which we cannot see, even in principle. But we have no reason to believe that the stuff out there is any different from the stuff we can see. And we don't have any evidence that it stops or wraps around. So, I mean, the usual assumption is infinite unless you're working in sort of early universe theory, and then you try and come up with models that create the universe in different ways, and some of those might be infinite or not. But it's not something we can test. What we can test is it uniform, and it seems to be as uniform as we can tell. We can test, does it have a curvature? It doesn't seem to have any curvature on large scales. We cannot test anything beyond the edge of what we can see, and up to there, we have no reason to believe it is or is not infinite, per se.
All right, well, thank you. So, with no more questions, I'd like to say...
Just light. Everything is based on observation. Is there a possibility that light's playing a trick somewhere along the line?
Possibility light is playing a trick. So there used to be a sort of cottage industry of trying to explain away the expansion of the universe or the acceleration with something called tired light, which was this idea that light would sort of change as it goes farther out. We have no evidence for that. It doesn't fit the data. So we learn a lot by looking at the spectrum of distant sources, we can learn a lot from the light being emitted from distant things, from the cosmic microwave background, and as far as we can tell, light acts just the same anywhere in the universe as it does here. So, yeah.
Well, I don't know about anyone else, but I've got a big headache after that. And I think the fact that we are slightly unstable explains a lot.
Okay.
Katie, just
yes.
say thank you from the behalf of the Space Association. We'd like to give you one of our pins.
Thank you.
And thank you so much for coming along tonight. And could you join your hands together and thank Katie Mack? So we're going to a break for about 15 minutes or so. The legs. Get a drink, go to the toilet, and introduce yourself to somebody you haven't spoken to before tonight. Good is to catch up with like-minded people. And we'll see you back here at 8:50. So that's 10 minutes from now, yeah? Thanks. Okay, welcome back. The room and the worldwide audience. We're back with now Angelo, Grazia, and Michael Abdilla, their monthly news session, news-based news. Just before I do that, I'll just mention something that someone just handed to me. In July at Melbourne University, there's a series of July lectures on Friday nights Friday 7th. Friday 14th, I assume. Yeah. 21st and 28th. So it's all on space this time. So we've got Professor David Jemison, Katie Mack, who we just heard from here, Michelle Trenti, and Associate Professor Martin Severe. So it's all related to space and space technology. So check out the. So okay, Angelo and Mike, and take it away.
Okay. Well, thanks very much, and good evening, everyone. This is our sort of update of what's been happening in space over the last couple of months. Our last presentation, I think, was in March, but we'd like to start in the Washington Roundup. What's been happening with NASA? As we spoke about it last time, NASA are going to receive about $19.65 billion. There's some winners and there's some losers. Planetary exploration and SLS Orion were the winners. Some of the losers was astrophysics, including earth sciences and education. So, not unreasonably, some of the senators are reacting to the cuts and trying to lobby the government to reinstate some of the money. The dilemma, whilst we've had a good budget this financial year, which is 2017, over the next 5 years, things are not looking so rosy. The budgets will remain flat, which means there will be a loss of earning power of about $3.5 billion. So if you're anticipating a Mars mission in the 2030s, might not really get up so quickly. We've got the Senator Ted Cruz, who you might remember from the election days. He's holding a hearing on the potential changes to the 50-year-old Outer Space Treaty. The objective, to better support commercialisation of space. So that'll be an interesting one, because that, was that no one owned outer space, and now all of a sudden people think that there's a dollar in it. And this is certainly going to be a hot topic over the next few years.
But that's not just an American thing. I mean, there's just
No.
one party to it. They've got to get all the other signatories to go along with it.
Yeah. At the moment, what they're doing is they're putting America's position into context, and then I suspect they'll call for a meeting and thrash this out. Now, Trump signalled his support to accelerate plans to send people to Mars.
Did he name them?
That was no, but I think he probably had a few suggestions. However, no additional funds were forthcoming. So the last one is the executive order to recreate the Space Council, headed by Vice President Mike Pence, is expected shortly. This is the SLS, the winner. Orion, the winner. I didn't put the pictures of the losers. Now we go into commercial crew. As you know, the Americans have been relying on the old faithful Soyuz to get their astronauts to the space station. And they want to get off that. And as you know, we've got two companies that have got the contract to provide astronauts to the ISS. The first one being Boeing and the second being SpaceX. This is just a list of targets, but as I'll talk about some of the milestones that were being mooted this goes back even to February, some of these dates have already shifted. The big question is, are the 2018 dates for crewed launches still feasible? Kathy Lourdes, who's the program manager at NASA, basically says a lot of things have to go their way to make that happen. Pretty tough, but not impossible. But she added, again, to give support to the two companies, private companies, so she's very impressed with how they're moving along. However, one of the placeholders for SpaceX, what's called Demonstration Mission 1, which is the first time they'll launch the Crew Dragon, is now in a document set to March 2017. 2018. My apologies, 2018. It was November this year. Okay. If you go to the SpaceX site, it's still November, but I suspect that slip really has happened. Boeing, commercial crew, key dates to look out for. January 2018, a pad aboard test Interestingly enough, they're not going to have an in-flight abort test. They're not going to bother with it. They reckon they've got enough data and enough certainty by pad abort to give them confidence that the CST-100 or the Starliner will actually fly off an exploding Atlas. The next milestone, next milestone is the uncrewed orbital flight test 1, they call it. It's on a ULA Atlas from Launch Complex 41 to the ISS. This is uncrewed. August of 2018, they launched the crew version. Then, after that, should they be successful, they will start their contract of delivering regular astronauts to the station. And that's what it looks like with the latest modifications to the skirt there to keep the dynamic stresses on the Atlas rocket down to acceptable levels. SpaceX commercial crew. Their key targets. March 18 was the uncrewed Dragon demo. That's gone to March 18. Early 2018, I think January was the last date I've seen, the Crew Dragon in-flight abort test. That'll be something to watch. They'll actually launch probably on a reused Falcon and then blow it up and see what happens. That should be interesting. Now, the actual manned flight is now probably, in my estimate, haven't seen this anywhere, is probably August. So they are slipping, but if you remember, there was a Office of Management budget assessment that said they're not going to be flying men into the space station until 2019, so this is still in advance of that. Okay, and that's a nice picture that I found of Crew Dragon on top of a Falcon 9, Pad 39. Very nice. And that's what it kind of looks like. General SpaceX, some key space activities. The first two in black have happened. And the ones that are coming up that you want to look for is CRS-11 coming up in a couple of weeks. Mid-June we have what they call flight proven, not a second-hand booster. We'll launch Bulgaria Sat, and the booster will be recovered on the barge. OCS, what's that stand? Of course, yeah, that's it. Late June we have Intelsat 35, no booster recovery because of its geostationary orbit and the heavy satellite. And the 30th of June from Vandenberg, we've got Iridium. So you can see within the space of 4 weeks, not even 4 weeks and a bit, we've got 1, 2, 3, 4 more launches. And that's pretty good. And there's other missions post that I haven't listed. No earlier than August 2017, wasn't mid-2017. Was Falcon Heavy, 27 Merlin engines, powerful rocket. They recently did a static test in Texas, and the side boosters will be the recovered boosters, that they're actually bubble wrapped and moving to the various processing centres. Falcon Heavy, as I said, no earlier than, what's this, Falcon Heavy? The Air Force test program. Very critical for SpaceX to get their Air Force contracts going, and they're still calling it September, but it'll probably be a bit later than that, where they actually launch a US Air Force payload to demonstrate that it's not just a United Launch Alliance that can do it. Then in 2018, we've still got the Grey Dragon, that's around the moon, free return trajectory, paying passengers, and 2020 Red Dragon, Mars landing, maybe 2. There was an article I read where they're thinking of perhaps 2 of them. One at the start of the window, the close start of the window, Mars window, and one towards the end of the Mars window, probably to give some redundancy. That'll be something if they pull that one off. And there we have
landings to be grouped or independent. Does the second one go off for the first one?
Good question. I suspect they will. To demonstrate the capability of landing objects close to an area so that they can build up on. The National Reconnaissance Office, i.e. Spy Satellite, was launched May 17. It was a great mission because for the first time we really saw great video of this thing. It was during the day, and it was just awesome to watch, and it's probably worth playing this. So bear with me, but it's great to see. Oops.
You have to look at the other screen.
Sorry?
We give the mouse to the right. Cursor to the right. Look at the screen. Move your cursor to the right.
To the right.
Keep going. There you go.
Where is it?
And the bottom, see?
Sorry, mate. Go on, you do it. I can't see it. No, it's not. My apologies. Stop. It's here. Let me try it. Yeah. Click. Give me this. No. Just give it to me.
I've got that little. There you go.
You couldn't see it.
It's so much on my mind, I don't know where to start. That light in your eyes, feeling down. So that's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Lift off.
There you go. I never get sick of watching that. That is pretty amazing. That was a great video. Good marketing too, I must admit. Put together by SpaceX. This is Falcon Heavy compared to Falcon 9. And there's the Falcon Heavy. And interesting, in Texas, not so long ago, they actually did a static fire test of the core stage. Now that core stage, if you know anything about this particular program, they first announced they were going to launch this about 4 years ago, but Elon Musk keeps saying that they really had a lot of difficulty in designing this core stage to be strong enough to carry the loads.
Is that a V's one?
That could, yeah, that's a good point. Maybe that's not the one, but they actually did do a static test of the core stage. And I don't think this is a side booster either, but it's bubble wrapped, and they do have two that they're going to be using for their Falcon Heavy. Again, no earlier than August, probably September, October they'll be flying this thing. Landing zone 1, 2 and 3. Now, all three boosters will be landing. The core stage will land on a barge, the other two will land back at landing zone 1. As you know, there's only one landing pad in landing zone 1 at the moment, but they will need to build by August another one. And they're planning on putting another 2, in fact, at the landing pad. So that'll be cool. And there's the grey dragon, and there's the red dragon. Nice picture. Then we've got Jeff Bezos, Blue Origin. What's been happening there? He's obviously procured some launch sites at Cape Canaveral, but he's recently been pushing the Blue Moon proposal, and it's really a heavy lift capable lander for the moon. In other words, to provide transport services to a burgeoning lunar colony, and he's going to launch it on a New Glenn rocket, and it's all part of that what I call the moon fever that seems to be going around at the moment.
What sort of heavy lift?
I don't know what the actual numbers are, but it will be of the ability of landing significant payloads to construct, facilities.
Can we assume between 50 and 100?
I don't think it would go that high. 50 maybe. 50? Okay.
I have pictures of...
I'll show you a picture in a second. But they did have a little bit of a setback. As you know, he's also, for his New Glenn rocket, he's developing a new engine called the BE4. It's also the front runner for powering the new Vulcan rocket. But unfortunately, he's had a power pack probably blow up.
Maybe you should take up the vanadium crystals and use dark energy.
Well, you never know. There's a lot of dark energy there, so there's plenty to be had. But
when they discovered dark energy, they had a Tesla-like one.
So the quote was not unusual during development, and I support that. Jeff Bezos, he sells another $1 billion of Amazon stocks. If you didn't know, that's how he's currently funding SpaceX. SpaceX. He's funding Blue Origin. And there's the supposed Blue Moon lander. It derives a bit of its technology from the New Shepard launcher, in fact. So, interesting. And there's the New Glenn rocket compared to the Saturn V. It's one of these monster-class rockets. And there's the Blue Origin factory, which will be finished by the end of this year, that starts producing these things. That's not far from the Visitor Centre, those that know Kennedy Space Centre. So it's well underway. And this is what it looks, the New Shepard, the suborbital. You can buy your tickets now. I think, Mike, next year, get a ticket, right? I don't know what the costs are, maybe 200,000, but you can go for a bit of a spin in this. It's just fantastic. It's the look of modern spacecraft now. Oh, and there's his little, where's that on the seat, is it? Aerojet Rocketdyne, like I said, there's two competitors that are running the Vulcan. As you know, the RD-180s, the government said, no, we're not buying any more Russian engines, therefore you've got to make your own, and that's where the BE-4 and the AR-1, and recently Aerojet tested it. It's gone through its critical design review and is progressing well. However, they are probably a year behind Blue Origin, but there is some of the injectors and stuff that they're testing. Orbital ATK, they launched AO7. Andrew, that's the one where those CubeSats went up? Correct. Okay, we'll talk about that in a minute, but that was launched in October. We've got Antares 8 going up in November, and 8 will actually be with the new Russian engines, the RD-181s, and then, because they used the Atlas for that previous launch in April. Then we've got 9 in November, and there's still a next generation launcher which they're talking to the US Air Force about, so don't know where that's headed. There's the Cygnus and the rocket there, and we have the next generation launcher. You know, it looks very similar to Ares 1, I think. Yeah, Liberty. Sierra Nevada, drop tests are finally being announced pretty much in June. So we'll see that previous version of the baby shuttle fly at Edwards next month, and the cargo version continues to be developed. That was the first drop test where one of the landing gear didn't come down, and that's what the cargo version looks like. Virgin Atlantic, they recently carried out some flight tests as well as testing of the feathering mechanism of its second Spaceship 2. This was interesting, the second point. If you want to get a ticket, you have to get in line, and you probably won't fly till 2021 because there's 650 people in front of you. So I thought, wow, that's a pretty amazing number. And they are looking at 2018 to start flying. I think it's optimistic, but Richard Branson's certainly putting the pressure on the design team to get it going, because it's been delayed for some time, as you know, from the accident that it had.
Branson's own words, first flight 2014.
Exactly. Anyway, there's the Spaceship 2. There is under the White Knight 2, and that's the Spaceship 1 in fact, but that's what the feathering mode is about. It basically turns the spacecraft into a shuttlecock that reduces its drag considerably and slows it down. And of course they're still working on their Virgin Orbit to launch from a 747. Lunar X Prize, the only development there was that Space IL from Israel has basically not pulled out, but it can't launch in time, it just hasn't got the time available, and it's hoping that X Prize will get extended again, but there doesn't seem to be any extension at this point. So that means by the end of the year, to get your prize, you've got to land a spacecraft on the moon, and I think you've got to traverse the moon for X meters or whatever it is and take a picture of a few things. So that'll be a good one to watch. Rocket Lab, I'm not going to say too much about it, but Rocket Lab is a US aerospace corp with a New Zealand subsidiary. Rocket Lab's mission is to develop lightweight, cost-effective commercial rocket launch services. I've heard anything from 250 to half a tonne. It's the 10-day launch window opened, I think it was the 21st, even though it was announced as the 22nd. So I'm sure Andrew will clarify that for us in a few minutes. But they apparently scrubbed on Sunday because of weather, and there was a hell of a wind blowing that day. And there it is. I'll go through this quickly because Andrew will cover this a little bit more. There it is not so long ago, and it's launching at the north east corner of New Zealand. And now we're going to Vector. There's a big hoopla about this thing. It's another suborbital. They recently tested the rocket. Again, it's the small satellite market. They launched it from the Mojave Desert launch site, but it only, last I read, I couldn't get any information, but it was kind of only went to about 3,000 feet or something. It was really just 4,500. Thanks, Mike. So it wasn't a really big deal, but they're progressing. They're raising money to continue the operations. So again, trying to build a rocket that will compete in the CubeSat small satellite market. Again, we explained this last time. They'll bring a box to your factory. You can load it into the box, and they will come and grab the box, and they will load it onto the rocket. And so you don't actually have to, integrate heavily with them. A couple of launch sites. United Launch Alliance, they're still working on the Vulcan. You've probably seen these before. This is the game changer in my opinion. It's a advanced cryogenic evolved stage. It's meant to be provide in-flight refueling capability and relaunch in space. What's the closest thing to what I knew as a space tug. So we'll see how this, and this is going to come about in about the 20s, mid-20s. And there's potential uses for that particular. Other space news. How long have I got? 13 minutes. Okay. NASA, now, I don't know how much of this I spoke about last time, but I'll whiz through it. The NASA administrator nomination remains pending. I think the administration's a bit sidetracked at the moment. Following a study on the issue, NASA has decided, for cost reasons, mind you, they're not going to man EM1. If you recall, the administration was asking, can we do something during this presidency to make America great again and fly some men around the moon? But NASA said, no, it's going to cost us too much and we'll delay the program. Incidentally, EM1 is now scheduled for early 2019. It was towards the end of 2018, has now slipped. That's official. Cislunar outposts are also being investigated. More announcements come out day by day on this stuff, but everyone's working on it. Cislunar space, like I said last time, is the area around the moon with the diameter of the moon's orbit. Highlights, a couple of others. The Kansas Cosmosphere Museum will restore the historic Apollo consoles down at Mission Control, which is good. And those who've done the tour at Houston, you can go in there and you can have a look at them, and it's great to hear that that history will be preserved. NASA has also extended its contract to Delaware North to operate the Kennedy Space Center Visitors Complex, and if you follow this, it's been going in leaps and bounds for years. They keep developing and adding, and they still have big plans to make that visitor centre bigger and better. It's worth a visit if you get there. Saturn V engines, if you remember, Jeff, some years ago, 2013, recovered some of the Apollo rocket engines. Do we know what Apollo that came from?
11.
I heard that too, but I wasn't sure. So these could be Apollo 11 engines of the first stage of the Saturn. Anyway, they've been refurbished and they've been put into a museum in Seattle. And they're not full F1s, they're bits of it. I'll show you some pictures in a sec. The last bit is, over the next couple of days, those CubeSat satellites, Andrew, that... sorry? So have they been... I didn't know that. Okay, excellent. All right, so they've been deployed. Well done. Again, the administrators. There's some bits of the engine, Len. Okay. So they've got the injector plate there and bits of the housing, but obviously the engine bells are gone. But they have been refurbished, so interesting. Now they're displaying apparently the whole of the Saturn first stage there as well. No, not recovered, just a real Saturn V, but these are the recovered bits. Now, NASA's been working on this kind of roadmap, Earth reliant, then the proving ground around the moon, and then go to Mars. This is the whole strategy that they're working forward to. Of course, none of this is funded fully, so it's just bits of paper at the moment, but this was a good thing that came out, was some of the missions. EM1, November will be early 2019. No crew. This will be the Europa Clipper. That'll fit maybe, could be 2022. Then we start this launching the rockets one a year to really build this lunar gateway. And there you have it. So they've got a sort of a plan up to exploration mission 11. But again, they're fleshing this out. They need to have a plan because they need to start building modules. This is a mission profile for first crewed launch of Orion, which is EM1. Not correct, it's changed again. That'll be right.
It's not crude. It wasn't correct. EM1's uncrewed now.
No, look, to be honest, I'm not sure whether that's EM2 or EM1. I'll be honest about it. Watch this space. Don't know yet. Cislunar Spaceport Outpost, again, we're going to the various low energy zones around the moon. There's a typical lunar outpost. Then something a little bit more extravagant that goes beyond the moon. And of course, all these companies have a hand in building lunar outposts. I'm not going to go into too much, but everyone's got a plan. I know one of the bits that the Russians were very keen on having some sort of orbit where they could land on the moon easily, whilst the Americans have got this low energy orbit that means it's harder to land on the moon. So lots of discussions going on about how to complement each other and work together. But private industry will play a big key in all this. And of course Boeing have got their plan. You've got Lockheed Martin have got their plan. ULA have got their plan. And Bigelow, of course, has got his, with the big blow-up components. On the moon, in orbit, space hotels. And ESA has been pushing this Moon Village concept. This is NASA Roscosmos, cislunar concept. So again, a lot of work being done. This is Axiom. They're actually going to launch a private component to the space station at some point. I'm not sure, Mike, any idea on the time frame on this particular thing? Yeah, well, when you write these things down, you do it with you do it at your peril. That's the module. Yeah, I think we showed that last time. Move ahead. Space Launch System, where are we? Okay, there's a lot of testing going on. Parachute testing, testing of modules, intracryogenic propulsion stages, SRBs, a whole heap of stuff. VAB has been completed, parachute testing, a service module that came from Germany, went through its paces. The big stands that were built at Marshall to test the core stage. You see bits and pieces of the SLS going in there. There's a huge core stage. There it is again. And here's the Pegasus barge bringing in the back end of the aft section of the SLS. That's without the rocket engines, but they're going to send that through its paces. There's the ICPS, intracryogenic, for EM1, already built. Solid rocket boosters, ready. And of course they've been test firing the RS-25s. They were going to launch one, or test fire one the other day, but they cancelled it. I haven't heard that they've refired it yet, so I don't know what the problem was. And these are the old stands when they used to use them for the Saturns, but they've all been repurposed. And there's the vertical assembly building, and all the platforms ready for the SLS are now up. Problems. What problems? First, welding defects were discovered. It's to do with the friction stir welding, so they've overcome some of it, but they've got some components that have got defective welds, so they've got to figure out what to do with it. So that's problem one. They damaged a liquid oxygen tank the other day. NASA and Boeing, they're still investigating the accident. Don't know exactly what happened, but they've seemed to have damaged that tank. Now, NASA has spent about $23 billion so far, not to mention the $9 billion that was spent to mothball Constellation. It needs another $23 billion to get this thing to its first manned mission in 21 or 22. Some say SLS is bigger than NASA can afford. Someone the other day asked how many Falcon Heavies you could buy for $23 billion. The answer seems to be about 80 Falcon Heavies plus about 80 Vulcans. Makes you think. The cost of the test stands also got a bit of a scrutiny, and the outcome by NASA's Inspector General was that it cost 87% more than it should have. And the reasoning behind that was that they had to meet a target of 2017, but whilst it was meeting the target, the rest of the SLS program slipped, and there were a lot of design changes. So budgets, however, are likely to be flat in the next 5 years. So there's still question marks in my mind as to how the SLS is going. Russia, Viktor Gorbatko recently passed away, and the reason I put him here is because he was one of the first group of cosmonauts with Yuri Gagarin. So it was sad to hear that he passed away. In the next few months, Russia plans to end its dependency on US satellites for comms with the International Space Station. Energia, there was one of the Russian guys was very doubtful that SpaceX could pull this 2018 Grey Dragon off. So he made a few comments. But what he did say was that after the Americans start going up in their own rockets, Russia is likely to sell Soyuz seats again. So you can save up your money for those ones. And also there was a comment that Russia believed it was cheaper to develop a new heavy lift rocket than revive the Energia vehicle. And I'm sure Igor could give you all the details of that particular issue. There's Victor. This is Federation, and is currently being developed in Russia, and of course the heavy lifter. So we're not quite sure where that's going, but that's certainly not funded, correct, Igor?
No, it's funded.
It is. And future?
Future is my separate
question. These are some previous heavy lifters you might remember. China. Now there's one to watch. I haven't got long, so I'm going to rush through this. China's space ambitions, and they're the upcoming kid on the block. But moon sample return launched this year, November. Moon rover 2020, far side of the moon. Planning a series of long-duration lunar simulations on Earth. Men on the moon by the 2030s. They're talking to ESA about the Moon Village initiative. Manned spacecraft, development of new space capsule to follow on from the Shenzhou will be used for moon mission. Space station. The Tiangong 2 launched in 2016 will slowly be upgraded. The Tianzhu cargo ferry launched in April, undertook refueling tests. So they're really broadening their capability. Other scientists studying missions similar to NASA's asteroid redirect mission, which, if you recall from last presentation, Trump had basically not funded that. So the Chinese might do it. There's a sample return. There's the re-entry capsule for that. There's Jade Rabbit. They're going to put something a little bit more sizable than that. Moon landing. Well, there you go. And there's one of the Long March. I'm not quite sure which one that is. There's a whole series of them. Shenzhou. This is one that they're working on. Very Apollo-like. This is the cargo transporter. This is the space station. And that's sort of a assembly. India, nothing much more to say than they're another Persian space power too. They go in leaps and bounds. Japan, there's a H2 rocket. They're currently developing that engine down the back, the LE9, to power its new H3 rocket in the 20s. So everyone's moving to redevelop rockets. The last one is the Sabre engine. This is, to me, is a game changer. They've just started to build a factory in the UK, the same place where they actually designed the Blue Streak rockets. Remember the ones they flew from Woomera? They've got a factory where they're going to actually test one of these engines. And a lot of the technology problems, such as the rapid cooling of the air coming in has been achieved. So this is a game changer. This is the 4-hour London to Sydney flight, or Melbourne. So if this comes off, this will be amazing. What a time. Enjoy your ride. Thank you.
Well, greetings, folks. Now, I was going to be in New Zealand now, and I've been celebrating a successful launch of a satellite. But what happened was there were high winds this morning. Now, when Angelo was talking about Sunday, he was obviously reading from American source material, which, of course, they're a day behind us, those Americans. So it was this morning. It's going to go up at 7 o'clock our time this morning, 9 o'clock New Zealand time. And it didn't quite happen because there were high winds. And I was going to have a movie showing Jeff Beck sort of being like a windsock in the wind, but you can't download movies apparently from a thing called Twitter. Anyway, I've been in contact with them. I was going to go there and so on, and they made it quite clear that, one, they weren't going to allow... So? Oh, so where do I have to put it? I dragged a whole lot over. You do it. Sorry about this, folks. Not even any pictures up here. You're going to have to do that for everything, are we? Alright. Okay, this is a media kit. They have been sending me the materials, including some stuff that isn't on their public website, but it's only available to the media. And this one explains why you can't see it. Because the Mahia Peninsula here is... It's not rolling.
Yeah, it's rolling.
Oh.
Use the scroll bars on the right.
That way. Okay. That's the Mahia Peninsula, and you can see the yellow area there is the area that's closed off. And from anywhere in the green area where the public can get to, or where the media can get to, there's no way you're about to see the launch pad, no way you're about to see the rocket going up, and if you're that far out, all you'll hear is something like a photocopier in an office sort of sound. Now, when it does go off, and the next try, by the way, will be tomorrow morning at 9 o'clock, 9 o'clock New Zealand time, and if it goes, it'll go up, head off down this way into an 80-something degrees orbit. And so they're closing off that airspace down there. And you're not allowed to take any boats into this area. And the media are asked to not fly drones for reasons they explain in their thing. So this is a little thing they've given out to the media. And that's the marine exclusion area. So if you wanted to go and sail your boat out there and watch it, well, you're going to be stuck out of luck and seeing it. So that's one of the things. This is going to be awkward if I can't. because I've got several more. Can you help me here with the PDF? I want to get the next 3 PDFs to file to do before we start the photo sessions. So basically they're saying, when I was speaking to them, they said, is that the second one?
There's all 4. There are 4 tabs.
Oh, okay, right. Okay, well, let's have that one then. So they said to me, they're not allowing any media in. Once it's successful, they will post on the media hub that they've set up for the media, movies and pictures and stuff. They said that if I did come over, I wouldn't be able to see the launch from anywhere. And I said, I wouldn't even get the 1 minute of glory before it disappears out of sight. And they said, no. They're not taking any media into their headquarters in Auckland, where the mission control is. So basically she said, you can come over, but you won't see anything and we can't talk to you. And besides, there'll be no interview opportunities afterwards, or very limited ones, because anyone who's anyone in that thing, as soon as it's successful, going to get on a plane and head off to Los Angeles, presumably to do all the media over there. Okay, so the flight is called It's a Test, and that's the mission patch for it. Now it's a rather strange name. For it, that's out at the launch site. This is a picture I'm showing you where it is, and tests and so on. So that's one of the things. And here's the timeline of events, which I won't go through in detail, but it shows you the countdown and then the launch and the way it's going to work and separate. The second stage is the part that's going to get into orbit. There's no actual satellite on it, and they are going to just, as I understand it anyway, from the limited amount of information they're given, is they're going to put the upper stage into orbit, but not separate a satellite from it. Now that may well change. Okay, Peter, how do we get the next one then? So we'll close that. Oh, right. Now that one we've already seen. And there. One of the things I did suggest to Peter to find out how we could find out when this is going to happen, because I had a feeling they were going to do this in secret, is look at the NOTAMs, the notices to airmen. And Peter, being an aviator, it would maybe his pilot friends would have access to it. But anyway, this is the NOTAM that's been issued for that, and showing where the airspace is being closed off. And again, the diagram with the projected flight trajectory, which goes down pretty much to the McMurdo control zone for Antarctica. So, and this is a closer up view here of the heading out from the Mahia Peninsula, which is not very far from Gisborne and a bit further away from Hastings. So that's one way to find out what's happening, is to look at the NOTAMs. And that one I think we looked at as well, so let's quit out of that and head into some pictures. Now, see, I can't see a mouse on here, so I want to open all these pictures. Now, okay, it's gone on there now. Right. This has been up on their website, publicly accessible for quite some time, and it shows the arrival of the rocket some months ago onto the Mahia Peninsula. They built a number of these roads themselves, and they upgraded some other roads as well. They provided high-speed internet to the community and the area, so the community didn't have internet before that. And this is out at the tip, at the launch pad. And, well, we were supposed to get some sound in this, but you have to make do with me.
Our main launch facility. Rocket Lab's Electron has just arrived to Launch Complex 1. weeks, we will be working on the launch vehicle and some integration facility, after which we'll have some testing of the launch pad and then launch. Okay. Now, I'm going to show you some of the pictures they've got in their media pack, which can figure out how to get these loaded. Try selecting. And now that should be going to a slideshow, which you can see. And that's still the video. Okay, thanks. You get all those pictures up there. Okay, we should be able to advance the pictures. Right, and that's in Los Angeles. And this is the crew. So they've got quite a few employees looking at the rocket. One of the engine tests they did. There's a lovely video which I haven't got time to show you of them flying. They've got a drone that's flying all around us during the hot fire. And this is just a few days ago out at the Mahia Peninsula. And alright, doesn't want to go forward, so I'll go backwards. I'm showing you the whole area. It's quite a beautiful area. This was in the New Zealand Herald on Sunday, yesterday. So the number, I like the one that says the number of times any nation's first rocket test has reached orbit, 0, and Jeff Bezos hopes to change that to 1. And this is in their facility at the peninsula. You see, it's about half the height of a standard like Atlas V, but it's still a substantial vehicle. They've got quite a complex control centre, and I've seen other pictures where it shows quite a bit. Now this is one of the first ones I was going to show you. It's a test, which is a rather unusual name for a thing, and that's the mission patch. We're all set to go, hopefully tomorrow morning at 7 o'clock, but the weather forecast for the rest of the week is quite good, so it's likely they will go, but they've set themselves a several-week launch window in which they could go, and if it doesn't go then they'll postpone for several months. Right. Now, let's get out of that. Well, I want to go. Yeah, awesome. Okay, get me out of that folder that I was in.
Okay, you want to get that from there?
Yeah, I can't see that.
See?
There we go. Okay, good one. Now, QB50. A few things on that. First up. This is the, sorry. This is from Heavens Above website, and shows the recently launched satellites, and down the, scrolling down here, see these objects down here? Now 1998, you say, hang on, this thing was launched earlier this year. How come they're listing all these QB50 satellites as 1998? Well, the answer is they do what they did with the Mir space station, and the Salyut space stations, and that is, if it's deployed from that space station, its co-star number, which you see here is like 1998 67 LK, is from the object it's deployed from. So, okay, it went up on the Cygnus, docked with the space station, taken through the space station, and launched on the Kibo module. It therefore gets listed as an International Space Station object, the first element of which was launched in 1998. So all our Australian satellites launched in 2017 are co-starred as 1998 objects. Now, which ones are our ones on this listing here? And I've got another one here that I can open. And again, I'll probably... Oh, yes, it opened. And there's a whole lot more of these you see listed down there, 1998 objects. Which one of those is ours? I do not know. However, that's the sort of orbit they're in. But you see how they're being catalogued as object A and so on. And the launch date is given as 1998, which of course is not the case for these objects. This doesn't even give the deployment date. Now, moving on quickly to and I think we've got sound for that.
Hi from space. My name is Thomas Pesquet and I've been on the ISS since last November. I'm excited to be here in the cupola today to talk about the QB50 program. In just a few minutes, we're going to begin deploying a constellation of 28 CubeSats from universities and organizations around the world. The QB50 International Space Station program, coordinated by the von Karman Institute for Fluid Dynamics and sponsored by the European Commission, was launched and will be deployed by nanoracks in their CubeSat deployment program here on station. The overall QB50 mission is a combination of work from more than 50 universities and research institutes, 23 countries, and 5 continents. Here on the station, our global collaboration is crucial for success, and we're very excited to be a part of this international effort. The QB50 satellites being deployed today by the NanoRacks CubeSat deployer will perform a detailed investigation of the mid-lower thermosphere during a 1-2 year lifespan. Each of the satellites will use one of 3 instruments: an ion neutral mass spectrometer, the flux probe experiment, or the multi-needle Langmuir probe. The mid-lower thermosphere is a difficult location to reach. It's too high for ground radars and too low for large satellites. CubeSats allow for multi-point measurements of the gaseous molecules in Earth's atmosphere, each just the right size to house the necessary equipment. The QB50 mission is the first real-time coordinated study of the thermosphere resolved in space, altitude and time on a global scale. The CubeSat data will then be used to validate and enhance forecasting models and improve our understanding of the physical processes taking place in the thermosphere. Beyond just scientific research, QB50 serves as a world leader for facilitating access to space, promoting education in space engineering and international collaboration. Teaming worldwide is key for reaching the challenging goals awaiting humankind inside and outside our solar system, and QB50 would have never existed if the participants didn't share the same vision. Congratulations to the QB50 program, the von Karman Institute, the European Commission, and NanoRacks for bringing this global mission to the International Space Station. Let's go send these satellites into orbit now.
Right, now, okay, I've got a couple of pictures of QB50 satellites, and if I can just call them up. Right. Good one. Now, this shows the deployment of these satellites, and if I can get the laser pointer to work, which I think is that button there. Australia, we have this one here, the University of New South Wales ECO, there, and it gives the deployment time there. And we have another Australian one down here, which is SUSAT from South Australia. And again, the deployment there. And then we've got the Inspire 2 from the University of Sydney. And again, the deployment time there. And all the other satellites, they've all been deployed now from the ISS through the Kibo module. So they did have a delay on the second batch to go out, but I think that they caught up because there was mention they were going to reach a mile for a few days' time.
So Andrew, those dates are wrong, the ones on the tape.
The what?
Those dates are wrong. They've all been deployed.
Yes.
Those days in the future. Today is the 22nd. Is that the scheduled time?
Oh, that must. Okay, look, I'm sorry I only got this late this afternoon, and I understood that was the actual deployment times, but maybe that's the projected one. They have a picture of some of them going out.
Yeah, So
and
I think those start out.
So this is Inspire 2 and its logo, and that's some of those QBs going out, but I don't know which ones. There's one of those one of these ones that's just deployed, and that's the SUSAT, the Sydney one, Sydney University, and that's ECO. Alright, now we'll get out of here and we'll go back up and a couple of movies. Hinode. It's 10 years been operating. Japanese solar satellite. This may be a satellite that you've never heard of, but it's an Earth orbit. It's been taking pictures you see for 10 years, quite amazing stuff, and it complements that being done by the Solar Dynamics Observatory and the stereo missions. NASA next year plans to launch a satellite called Solar Pro Plus, and here's a little short graphic of it working, approaching the sun. So that's going to be launched next year. It's well under construction. You can get off the net time-lapse movies of the assembly of it.
How close does it get to the sun?
Huh?
How close does it get?
Very close.
It's okay, it's going to go up night.
Here's a graphic. Here's a graphic showing the planned trajectory. So it'll be well in the way of the coronal mass ejections and other things that happen on the Sun. And here's an animation of the overall trajectory. Now, for more than 30 years, I've been planning to try and get a mission that goes really close to the Sun, and for the first time, it's actually happening. You see, oh, she's going to get rather scorched. Discover. Do you remember Al Gore's satellite that was going to look at the Earth? And it finally got put up after being in a warehouse for many years. Well, this is the sort of thing it's been taking a picture of. This is the Indonesian solar eclipse, which you see several times over. Get the point? Well, there should be sound now. Oh, maybe not. Yes, there is. By the way, that website there, geo.world, has quite a few interesting videos if you're interested in earth sciences and stuff like that. Now, I'll just see if I can close that out and get rid of that one as well. Right, now, there's a couple of videos I'd like to show, but we won't because I can find the cursor again. Oh, there it is. I'm going to just flick into the slides now, and we'll race through those at a breaknecks. Oh, I can't get that over as well. All right, we'll just show the first step part. All right, here we go. Cassini. As you know, it's coming up on the final finale, and we have got a number of interesting things it's done over the last 13 years in orbit. Yeah, thanks. And the orbits in grey, it has completed. It is now in about the third of the orbits in blue, which are the final ones leading up to September. It's doing about one orbit a week at the moment, and it has made several dives already through the in the gap between the rings and the planet. Over the last 13 years, these are the orbits that the Cassini spacecraft has been making, and they're colour-coded according to different epochs in the mission. There was the prime mission, then the extended mission, then the solstice mission. So here are the grand finale orbits, and you see it's now in the ones in blue, diving between the rings and the planet. You'll notice over here, we've got the sun out here, and the Earth's pretty much where the sun is, and there's a shadow of Saturn goes back here, and it is going through the shadow areas, and so we said looking at the sun being occulted by both the rings and the planet, and that's providing further additional ring information as we go there, particularly for the radio science experiment. Radio science, where they track the radio signal from the spacecraft. The final one in red, says final orbit, is the one on September 15, when it finally enters the atmosphere of Saturn. A couple of recent pictures. This is the hexagon at the top of the at the North Pole, and Linda Spiker, the mission scientist, said just a few days ago that no one yet understands how that is formed and why it is so stable. So don't ask me why it's stable. It's a jet stream of some sort, but why it's that shape and why it's so stable, no one knows. We are now just a few days past the summer solstice for the Northern Hemisphere. As a result, the shadow of the planet is now not even covering the whole of the rings, so the outer rings out here are in sunlight continuously as they go around the planet. But this shadow here, as we head back away towards the equinox over the next few years, that shadow again will increase, but we won't be seeing it because, of course, the mission will have finished. But we did see the reverse happen as we didn't. So it's been around at least half a Saturn year now. That's been an orbit. All right. The propellers. Little tiny moons are here. And this one there. This is one called Grazia. All these propeller-shaped things are named after aviators. So we've got Earhart, Blériot, and so on. Goes on. Don't know if I got Kingston Smith or not. Anyway, the little moon there causes a perturbation in the orbit of the ring particles alongside, going past it, and give these particular interesting shapes. There are heaps and heaps of them, and you can see here, there's a group of them, swarms of them, they're all over the place. In addition, we can see some gravity waves, not gravitational waves, gravity waves in the rings. And we don't have time to talk about why they are formed. The final Titan flyby has happened. In fact, that's the one that diverted it into the final grand finale orbits. And some new findings have come out from that, the last few flybys of Titan, including some clouds in the atmosphere, and you can also see some of the lakes at the northern hemisphere there. Remember, it's now approaching summer on Titan, its northern hemisphere, and as a result of the heating, those lakes are evaporating away, and this cloud's forming, and presumably material is going to be dropping down into the southern hemisphere where it is now approaching winter.
What's the liquid in the lake?
Mainly ethane and methane. So if you want to fill up your car with LPG, just head up over there. Okay, and there's another picture of the clouds. Now, moving in again to a solar system, into Mars, and the Lunar Reconnaissance Orbiter, which has been orbiting the planet for quite some years, has taken another look at the landing site of Opportunity. Remember the hole in one landing? And we see here, as you can see from the caption, the lander bounced on the surface and rolled into this thing here before the airbags unfurled, and there we have the Eagle. Over here, we see the back shell and parachute. Yeah, so it's pretty amazing, all this flat surface here and it lands in that thing there. So that's a new photo that's just been taken in the last few weeks. Where has the craft been? Well, the answer is, rolling down here now, on a Mac I can press Command, so I'll try Control plus if I can see plus there, and see if I can enlarge that.
There's a zoom button up top there.
Zoom?
Big screen, have a look at the screen. The big screen.
Yeah, okay. Oh. Okay, good. So zoom it in. Right, that's perfect. Right, now you can see it here. And yeah, okay, so we've been exploring along the rim of Endeavour crater, and I'm going back in time here. So we follow it down, and it's done quite a bit of driving. You see, in just a few days it went quite a long distance. Most days it only drives a couple of metres or a few centimetres, but then other days it can drive 100 metres or more. And it's now going to head up into this area here and explore this area here. Right. Going to rush quickly on. Oh, it's just one of the ones that doesn't go forward if I've enlarged it. Yeah. Okay, I won't enlarge that. Then that shows got a nice little detail. That's the view from the rim of the crater, looking out in the distance there, and another view on a reasonably clear day. And that there, that's very good on stereo. If you can see, get yourself a stereo version of it, including the distance. There's the far wall of the crater over here, Endeavour crater. It's about 22 kilometres in diameter, that crater. So Opportunity is still doing well. It's left Cape Tribulation. And this is one of the last views that is left there. And again, if I enlarge it, you see the tracks going all the way up here and over the ridge. Yeah, so time's run out. But it's still doing a lot of close-up science of the rocks. Now, just where it has been, Cape York, it came in from there, has gone down past here. We've spent a long time here at Cape Tribulation, and is now leaving that and heading down towards Cape Byron. Those points are named after Australian points, and here is where Curiosity has been since 2012, trundling along. And this is a view of Curiosity recently, looking towards Mount Sharp. But don't expect to find every day you're on Mars. That's a view from Curiosity had a few weeks ago, and you can see there's a lot of dust and stuff around. And hydrogen on Ceres, the dwarf planet Ceres, and we've got some hydrogen showing there where the hydrogen is, and that means probably water, but the spectrometer detects hydrogen per se. And just to finish up, we have got a new moon has been discovered going around the third largest dwarf planet in the Kuiper Belt. So we've got Pluto, Eris, and then this one which has not been given a name yet. Now, it's a fascinating story which will take about 20 minutes to tell, which I'm going to tell on the radio in a few days' time, about how that was discovered using 3 satellites. But it's quite a mix of serendipity, missed opportunities, and so on. And there's some of the Hubble Space Telescope pictures of this dwarf planet and its moon. All right. Well, we better finish up there, even though we've got more to go. And there's always more to go. So,
thanks, Andrew. That was fantastic as usual. And that brings this month's meeting to a close. I'd like to thank all the speakers and everyone involved tonight. Obviously, Katie Mack, she's now gone home, but anyway, it was really great to have her on. Michael and Angelo for your views this segment, and Andrew, of course. I'd also like to make special mention of our crew, of our tech crew, Ashley. So, obviously, a huge production going on here, so I really appreciate you guys taking this effort, and it's working really well. And we had some people coming in on the stream and the obviously watching it, so it's fantastic. So, all power to you. So that's it for tonight. The weekly radio show goes to air as usual, 7 PM on Southern FM on Wednesdays. And our next meeting is June the 26th or something. 4th Monday of the month anyway. So we'll see you there. We haven't got a schedule for what's going on, but there'll be something interesting about. We'll find out. Oh, of course, this is coming Friday. Of course, the Australian Space Special Forum in Sydney. It should be a great night. Once again, if you go to Eventbrite, go to our website and follow the links. Book yourself a ticket, people here going. Should be a great night. If anyone is coming along and would like to help out, that would be much appreciated as well. We're going to have possibly 120 people there. Even if you're just standing there with your banjo on or talk about the Space Association, it would be much appreciated. Anyway, I'll stop talking and good luck.
Let me tell you one thing. I don't know how many of you signed on the first ever Into Space for the public names, but it's on the Cassini spacecraft, and I found out about a month or so ago, I was going to show this last month, the fitting of that CD-ROM with our names on it onto the spacecraft. First time I'd ever seen that.